I go by the name of Phaladi. I'll be taking you through the research paper with authors Amanda Phaladi and Thipe Modipa. So the title of the study is the evaluation of a code switch Sepedi-English automatic speech recognition system. In the presentation, we're going to go through the introduction of the study, the background, code switch speech corpus, system development, result, conclusion, as well as the references. Speech recognition is defined as a technology that empowers the machines to comprehend and interact with the spoken language. This capability has changed how we interact with devices and systems. Automatic speech recognition is a technique used to bridge the gap between humans and machines by facilitating a smooth communication and interaction through spoken language. However, the research landscape in ASR has mostly focused on languages with extensive speech data, and this focus has led to a notable progress in those languages, but it has also led to a gap in the exploration of ASR for languages with limited resources. And the task of handling code switching becomes challenging, particularly when it is applied to languages with limited resources. Hence, this study aims to evaluate the ASR system for code switch languages with CTC approach. Recently, there have been a significant advancement in ASR due to innovations in machine learning, natural language processing, as well as deep learning. CTC approaches has contributed to ASR advancement and has shown good accuracy improvements. The attention-based model can achieve state-of-art performance in ASR, but they can be more complex and computationally demanding than the CTC-based model. Hence, we chose to use the CTC approach. Transformers are yet another deep learning architecture. They have the ability to capture complex sequence-to-sequence patterns, and this capability has led to improved performance across a range of tasks, including ASR. Connectionist Temporal Classification is a technique used in ASR and other sequence-to-sequence tasks. In this study, CTC employs greedy decoding during inference to predict most likely output sequence for new input data. Greedy decoding computes its output by finding the most likely symbol at each time and match the repetitions in the sequence. This is proven by the picture which is shown below, which shows us the frame-wise and CTC network classifying a speech signal. So if you can look at this picture for CTC, we have the dotted lines, which shows us the probability of the blank symbol. We can see that most of the time, the probable symbol just happened to be a blank, and the correct symbol pop up where it's supposed to pop up. So by simply getting a greedy decoder and compressing it, it will give us the desired output more often time than not. So on the code switch speech corpus, in the study, we've used two different data sets, which is the Sepedi Prompted Code Switching corpus as well as the NCHLT Sepedi corpus. So the SPCS corpus has approximately 9,183 audio files, of which 8 were recorded by males and 6 were recorded by females. And then below we have two distributions, which the first one shows us the SPCS utterances. So amongst 9,183 audio files that we have, 74.6% of those were used as training, 13% were used for testing, and then we've used 12.4% for validation. And then the other distribution shows us the words per languages. So we have 43.9% of the words in the SPCS corpus, which are English words, and then we have 48.7 which are Sepedi words, and then we have 7.4 which are recorded as others. They're recorded as others because they are borrowed words. And we're talking about when we are talking about borrowed words, we are talking about the words which cannot fit perfectly into the grammatical patterns of either of the languages. In our case, which is Sepedi and English. here we're going to look at the testing data. So the testing data was taken from the SPCS corpus as well as the NCHLT Sepedi corpus. So the NCHLT testing data was composed by 4 speakers, of which two were females and 2 were males. And then the table below just shows us the distribution of the utterances per corpus for different genders. And then on the system development, during the model setup, we defined the network architecture and we specified the necessary input-output layers. And during training, we fed the model with input-output pairs from the SPCS data, and we ran the model for fixed number of epochs. So below are the system parameters which were configured during the model setup. So everything here was fixed, the RNN units, the kernel size, learning rate, dropout rate, as well as the epochs. The only things which we were changing in our experiment were the number of filters. So the number of filters that we use 16, 32, as well as 64. So the number of filters determines how many different features maps will be produced by the layer. So when we set the filters to 16, the convolutional layer will have to scan the input data and capture 16 different types of patterns. More number of filters means that the model can capture a large variety of complex patterns. So for evaluation, we used the word error rate to measure the accuracy of the system. The word error rate measures the difference between the words in the predicted output and the words in the reference text. The formula to calculate the word error rate is the one that is shown below, where the S represent the number of substitution, the D represent the number of deletions, the I represent the number of insertion, and the N represent the total number of words in the reference text. The graph displays the validation loss and the training loss for experiment with different number of filters. The validation loss represents the loss that is measured on the validation set, and the training loss corresponds to the loss that is calculated on training set. Sorry. So for 16, when the number of filters is 16 and 32, we can see on the graph that we have a plateau from epoch 20 as the training loss continue to remain flat and decreases slightly. So this means that the model has learned the underlying pattern of the data that we used, and it's able to make the correct predictions. So the lowest loss that we got when we were using 16, it was 21.96, and then the lowest that we got when we were using 32 filters, it was 22.22. And then for 64, the lowest loss is 22.82. And this graph shows the noisy movements, and it can be caused by the complexity of the model. So for all the experiments, they start with showing a good fit because the training loss, we can see that it's closer to the validation loss. This figure here represents the word error rate across different number of filters during the validation phase using the SPCS corpus. So the minimum word error rate is achieved when we used 16 filters, which gave us 41.9% word error rate, and we got 43.48% when we used 36 filters. And then for 64 filters, we got 47.47%. So the model's performance was best when we were employing 16 filters, which indicated that for this data set, a smaller number of filters in the convolutional layer was advantageous. And the word error rate increases as the number of filters increases, and this suggests that the model had become complex for this data set. For the testing data, for NCHLT, we have high word error rate, This shows that the system was trained on a set of different data, which is different from the NCHLT. Hence, we get a higher word error rate as shown on the table. So we can say that this shows the difficulty of generalizing different unseen data. For SPCS data, we got much lesser word error rate compared to NCHLT, and this is because the ASR system performs better when training and testing data are closely aligned in terms of the domain and the context. So in conclusion, this paper discussed the evaluation of code suite ASR system for Sepedi and English using the CTC approach, and the CTC-based model was able to achieve 50.05 word error rate on the testing data of the SPCS corpus and 84.59 on the NCHLT corpus. So more experiments are needed for different code switch corpus, and the results of the study serve as a baseline for future code switch ASR system in low resource language, and future work will include optimization, ASR system evaluation of monolingual Sepedi dataset for generalizability and practical application accuracy. So those are some of the references which I used, and this is the end of my presentation. Thank you.